Hi everyone. So this is a brief introduction into stoichiometry. So stoichiometry is the study of us understanding how we can look at the amounts of material being involved in chemical reactions. So if I look at a very simple reaction, so let's say I want to add hydrogen plus oxygen to get water. Right? Brief reminder, hydrogen and oxygen are both diatomics. Remember, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. All 7 of those elements have to be diatomics, H2O2. So if I look at this reaction, we know the first thing we do when we're working with a chemical reaction is we have to balance it. So I have 2 oxygens here, 1 here. So I'm going to put a 2 in front of water. 2 times 2, I have 4 hydrogens, only 2 over here. So I'm going to put a 2 in front of my H2, and now I'm balanced. So in looking at this particular reaction, what it's telling us is if I mix 2 hydrogens with 1 oxygen, I get 2 waters. Okay? So this works great for us understanding this on a molecular scale. But if we're doing this reaction in a lab, we cannot just go to the back of the room and say, get me 2 molecules, get me 4 molecules, 6 molecules. Right? Those numbers are all way too small. We cannot measure that on an individual basis. So what I want to do is, what happens if we scale this up? So right now we know we have a ratio of, for every 2 molecules of hydrogen, we have 1 molecule of oxygen to give us 2 of water. What if I double that, right? 4 hydrogens gives me 2 oxygens to produce 4 waters. Let's keep scaling it up. Let's go up by a factor of 10, right? 20 molecules of hydrogen mix with 10 oxygens to give me 20 waters, right? I can keep scaling this up. I can even go up by 1,000 and say 2,000 hydrogens plus 1,000 oxygens give me 2,000 waters. I mean, that seems like a lot, right? 2,000 seems like a large quantity, but when it comes to individual elements and molecules, way too small. We still cannot measure that. But the one scale-up factor that we've been talking about throughout the year is the mole, right? The mole is a huge scale-up factor. Remember, 1 mole is equal to 6.02 times 10 to the 23rd of that object. So instead of saying 2 molecules of hydrogen, 1 oxygen gives me 2 waters, I can say and scale up by that factor of 10 to the 6.02 times 10 to the 23rd, 2 moles of hydrogen mixed with 1 mole of oxygen gives me 2 moles of water. So these coefficients that we see in front of the balanced reaction are referencing the relative mole amounts of each of the substances within a reaction. So I'm going to rewrite the reaction. We're going to keep working with the same one here. So what I want to think about is, how can we use that information to start predicting, let's say, how much product we're going to form. So let's say I have 5.6 moles of oxygen, and I want to figure out how many moles of water will I be producing. Well, I know that there's a conversion factor in here, right? And that's all going to be based off of the coefficients. There is 1 mole of oxygen per every 2 moles of water. Remember, if you don't see a coefficient in the balanced equation, it's assumed that that number is 1, right? We just don't write that. So again, 1 mole of oxygen converts to 2 moles of water. So when I do that math, just 5.6 times 2, I'm going to get 11.2 moles of water. And so that's it, right? That is the meat of stoichiometry, being able to convert from moles of one substance in a chemical reaction to moles of a second substance. So remember, you always need to have a balanced reaction. If that is something you're struggling with, I highly, highly recommend going over your notes from those units, coming in, asking questions. I can help point you to directions of extra practice to help you with that. But you've got to be able to balance your reactions because those coefficients are what are the meat of being able to understand these ratios. So once we have our balanced reaction, all we're looking at doing is looking at the ratio of the coefficients. And that's it. So let me give you one more example. So let's say I have, let's see this reaction. So I'm going to balance this reaction. I happen to know I have to do that. That gives me a 16 oxygens plus 1026, so 13. Right. I know I went through that pretty fast because I'm not using that as the purpose of this video, but I wanted to show you an equation that's a little bit more complex with respect to balancing. So let's say my question is, I have 0.5 moles of my C4H10, and I want to know how many moles of water am I going to produce. So I started with what I'm given. I'm given the 0.5 moles of C4H10, and then I do my conversion. So I know I want to get rid of the moles of C4H10 and convert to moles of water, right? That's what I'm trying to solve for. So if I look, there's a coefficient of 2 for C4H10, so that's going to go here. There's a coefficient of 10 for water. That's going to go here. So then I end up with 0.5 times 10 divided by 2. So 0.5 times 10 is going to be 5. Divided by 2 is going to give me 2.5 moles of water. And that's my final answer. So this is looking at the meat of stoichiometry, which is the mol-mol conversion involved. Later videos will help us show how we're going to start integrating gram and other calculations into this as well. Let me know if you have any questions.